Hi everyone, Mr. Lee here. In this video, we're going to go over the uniform circular motion, or UCM for short. Alright, now to start off with uniform circular motion, let's just go over the basic definition of what UCM is. So if you have an object that is undergoing universal circular motion, what this tells us that it is just constantly moving in a circle. Okay, well, as the name implies, uniform circular motion. This is just like an object just spinning around and around and around, kind of like a merry-go-round, or let's say a CD that just spins around, or a record player that spins around and around and around. Okay, so universal circular or uniform circular motion. This can also apply to like things like tires. I'm just trying to think of different examples that you might see. So tires, and even our moon itself, and including the Earth, which orbits around the sun. Okay, so let's get into it. To really dive into the uniform circular motion, we have to actually take a step back. Let's go back to the velocity equation. So velocity, if you remember, it was the displacement over time. Okay, velocity was the change in position over the change in time. So for uniform circular motion, we are going to use an equation very similar to this velocity equation. All right. Instead of v for velocity, I'm going to introduce to you a new variable. This is omega. Kind of looks like a W, but there's like a little hole in the middle. Okay, omega is equal to, okay, so omega, so I'm going to take a little pause. Omega is what we call the angular velocity or the rotational velocity. Okay, so it's how fast something spins around. So angular velocity or rotational velocity is equal to, so instead of saying displacement, we have to think, if we have an object, right? We have an object, and here's like the center of its rotational path. Okay, so I'll do this in a different color. Let's do this in red. All right, so let's say we have an object out here, and this object is spinning around in this circular path. Instead of looking at the path that it takes, which would be delta x, we will see the change in angle. So if we start off here, so we'll call this position 1, and we can call this position 2, we can say that the change in rotation, okay, because it's rotational velocity, or the change in angle between 1 and 2, that is our new displacement. And we call that the angular displacement. So this shaded, okay, I'm shading it in, okay, that shaded little section of the circle is our displacement. And we call that delta theta, okay, or the change in the angle over the change in time. So it's very analogous, it's very similar. If omega, or angular velocity, is similar to our regular velocity, our delta theta, okay, our delta theta is very similar to the change in position or displacement. So it's how much the circle or the rotation has changed. And well, time is just a universal value, so there's no rotational variable for time. Okay, so this is our very first equation. I'm going to highlight that because that's very important. Okay, and the next thing you need to know are about the units. So the units for time is just seconds. Okay, I'll do that over here too. The time for the time and velocity is just seconds. Okay, and the delta x, the change in position, the units are meters. Okay, so we have the units for velocity as meters per second. Now, if we take a look over here, the units for time is still seconds, but the units for theta, delta theta, when we're talking about rotational velocity, it's going to be in radians. Radians. Okay. Now, I just want to pause right here. This is one of those red light moments, right? Important, important, important. A lot of times students see RAD or radians and they think about radius. Okay, so I need you to know that radians is not the same as the radius. Okay, radius is a unit of distance. okay, or how far it is from a center. So it's like a distance or a displacement. But radians is the it's like the angle, okay, or how much of a circle, like that section of a pie. Okay, so these are not the same. Radians and radius are not the same. Another way to distinguish this is that radians, these are the units, and units include stuff like seconds, newtons, what else do we have? Meters per second, and now we have radians. So if we were to go off of these units, radius, which is a unit of distance or displacement, that's our variable. So variables, they pop up in the equation. Okay, so these are what we use in the equations, and the variables are what we use to replace numbers with. Okay, so instead of seconds, we would have time. Instead of newtons, we would have force. Instead of meters per second, we would have velocity. And now instead of radians, we would have delta theta. Okay, so this is our very first equation. Uniform circular motion is how much the angular displacement changes over time. All right, so with this, we can come up with a couple of different kinds of equations. Now, these are just unit conversions. So we have an equation of omega, or angular velocity, is equal to the delta theta over delta time, or the change in rotation is equal to the change in time. Okay, and so the units are radians per second. Other kinds of numbers that you might come across are stuff like rotations, or degrees. Okay, degrees. All right, so you need to be able to always convert to radians per second. This is our SI unit. This is the standard unit, much like how we can't use centimeters, but we can use meters, right? So we have to convert from, get rid of that, centimeters to meters, okay? Much like how we can't use kilometers or kilometers, we have to convert to meters, or how we can't have hours, we have to be able to go from hours to seconds, okay? So we have to be able to use radians per second. And this is important because all of our variables and all of our units are linked to SI units. So if you're like plugging this in mathematically, you might come across an incorrect answer because the correct answer is in SI. So it's important to convert. All right, so we got to think about this in terms of radians per second and rotations per second. All right, so if we have one full rotation, okay, so one rotation in terms of degrees, if we have one rotation, we have 360 degrees. And in terms of radians, that'll be 2 pi radians. Okay, so this is our converting, this is what we're going to use to convert our numbers. Okay, so if you have rotations, we always want to go from rotations to 2 pi, or radians. Okay, if we have degrees, we want to go from degrees to radians. Okay, so everything gets converted into this radians right here. So let me show you how to do that. All right, if we have like problem that says a object rotated, I don't know, let's say 3 times, right? So we have an object that rotates 3 times, and we want to go from 3 rotations. Okay, so our conversion currently is 3 rotations, and we want to convert that into radians. This is how you do it. So when you take a look at this, if you have 3 rotations, technically it's in the numerator, right? So this is 3 rotations per, I don't know, over 1. Okay, so every number that you have is technically in the numerator and it's over 1, but we don't write it out, right? We don't write the number 3 like this. We don't write it as 3 over 1 because there's no point, right? Anything over the number 1 is itself. But I find that it helps to think about it in this fashion when you're converting. So if you have rotations in the numerator and we want to get rid of this rotations, right? We want to get rid of that value. We need to have rotations in the denominator. So I'm going to put rotations in the denominator. And in the in its place, when we cancel out and we multiply across, remember this is not called cross multiplication. Cross multiplication implies that you're doing numerator to denominator. Okay, we're multiplying across. When we multiply out 3 rotations over rotations, the rotations will cancel out. And so what we need to do is, in its place in the numerator, we need to substitute in what we want. So in this case, we want radians. So we can say, and so this value right here, it has to be the ratio that we're given here, because all of this is a 1-to-1 ratio. So we say that in 1 rotation, we have 2 pi radians. Okay, and then we multiply across. Once again, it's not called cross multiplication. Please don't call it that. We're multiplying it across. So it comes out to be 3 rotations times 2 pi radians. So I'll write it out. 3 rotations times 2 pi radians, all divided by 1 nothing times 1 rotation. Okay, over 1 rotation. So this is what our math looks like before we cancel stuff out. I know I canceled it out here, but let me show you exactly what that means down here. So the rotations, they cancel out, and we're left with 3 times 2 pi radians. So our answer would be 6 pi radians. And remember, the radians are the units. So we successfully went from 3 rotations to 6 pi radians. Okay, so we can get a little bit more complicated than this. So let's say something very common for like old school records is this RPM, right? RPM stands for rotations per minute. So if we have something like, I don't know, 60 RPM, so 60 rotations per 1 minute, all right? Rotations per minute. And we want to convert that into radians, radians per second. This is how I would approach it, okay? I'm going to first start off by mentally choosing, what do I want to first convert? Well, we did rotations already, so let's try that. So we don't want these rotations anymore. We want radians. So in order to cancel out this rotations, because it's in the numerator, I'm going to put in the denominator. And I want to put in the numerator, the opposite side, what I want to convert to. So rotations to radians. I know that for every 1 rotation, we have 2 pi radians. Okay, and at this point you can multiply out, and that's what I like to do. I like to do things 1 step at a time. So we get 60 rotations times 2 pi, which gives us 120 pi, okay, divided by 1 minute. Okay, so if you want to see the mathematical hoops I jumped through, I know that the rotations will cancel out, and so the only units that are left are my radians and my minutes. So that's how over here I would get 120 pi radians per minute, because these are the only 2 units that are left. All right, we're almost there. We're halfway there, in fact. I want to go from radians per minute to radians per second. Okay, so we already have radians in the numerator, so we don't want to touch that. We want to convert this minutes. I don't like the minutes. I want seconds. So in order to cancel out the units of minutes in the denominator, I have to put in the numerator, minutes, okay? And then in the other side, in this case the denominator, I want to put the units I want to convert to, so seconds. So in 1 minute, I have 60 seconds. Okay, and then if I were to cancel out units, the minutes in the numerator cancels out with the minutes in the denominator, and that leaves us with 120 pi radian times 1, so 120 pi radian, divided by 60 seconds. Okay, if we plug that into the calculator, we can see that that is 2 pi radians per second. All right, so we have this as our final answer. So you can do this. I just showed you how to do it with radians, but this also works with degrees. So for example, let's say we had, I don't know, 270 degrees, okay, and we want to convert that to radians. You just make it over 1, and we put the units, so in this case degrees, in the denominator, okay, and we put what we want to convert to, radians, in the numerator, because it's on the other side. And we say that for every 360 degrees, we have 2 pi radian, right? And let's see, if we were to do this math, we know that the degrees cancel out. And let's see here, 270 divided by 360, what is that, 3/4? Yeah, so we get 3/4 times 2 pi radian, which gives us 6 pi radian divided by 4. You might have to check my math on this, but this turns out to be 3 pi radians divided by 2. Okay, and so we successfully went from degrees to radians. All right, so that is our introduction into uniform circular motion. In the next video, I'm going to go over centripetal acceleration. See you next time. Bye-bye.